This video is a summary of what we've learned about graphing so far. And we really started out with situations where we were going constant speed during any given time interval. So all of these segments here are linear on our position graph, and that means as time passes, our position is increasing constantly. So in that situation, our velocity time graph looks kind of like this, little horizontal pieces. So just as a review, this is a relatively steep slope that corresponds to a fairly big velocity. No slope, that corresponds to no velocity. Same slope as before. So we're like that. Still positive, but not as much. And then this last part, very steep negative slope. We could hopefully go backwards the other way. This is a big velocity, so a relatively steep slope. Less of velocity, so a shallower slope. Then negative, something like that. On these type of graphs, our accelerations are not very important because over each period of time, we're going constant speed in each period. So we have an acceleration of 0, an acceleration of 0, acceleration of 0. Clearly something big happens at these points to make our speed switch, but that's not something we're looking at. So that's the first type of graphing we handled. And some of the problems are going to look like this. You can identify them if the velocity has a horizontal graph or if the position has a linear graph. Those are constant velocity problems. What we now have seen is situations where our position time graph has a curve. The fact that this starts out with a fairly steep slope, the slope levels off towards 0, indicates to me it's slowing down. So we will have accelerations here, and our velocity graphs will not simply be horizontal lines. They will be changing. So before we deal with these types of problems, which I think we can call constant acceleration problems, at least over these individual time periods, I want to go back and look at very simple linear velocity time graphs. And I want to make sure we understand how we can go from velocity to position and from velocity to acceleration. So first things first, on a velocity time graph, it's linear. So it tells you two different things. Y equals mx plus b, v equals at plus vo. We should be able to read our original velocity, that's the intercept, and we should be able to read our acceleration, which is the slope. Our acceleration here is the slope. Notice it's positive, and notice that it's not changing. So our acceleration versus time graph here is horizontal. We also know that we started with a positive VO. So what does that translate to here? I need to start with a positive slope since velocity is the slope on a position time graph. And my velocity is increasing, means my slope is getting steeper. So that's the position time graph for this situation. This is an object that's already moving and it's just going to get faster and it's just going to keep going in one direction. How about this one? Well, here we have a negative acceleration. We have a constant negative slope. We have a positive VO. So what's this? We're still going to start with a positive slope, but my velocity is decreasing, so my slope should be decreasing. And it decreases to 0, which means we get to this point. Then my velocity continues to decrease. Now it's actually speeding up but in the other direction. So this is an object that slows down, stops, and then turns around. And that's what our position time graph shows too. Where I started these is arbitrary. I don't know anything about original position. I'm just always going to do it here to make it stay constant. But without outside information, we could start at any location we like. Okay, this one, we have a negative VO and a positive A. So our acceleration graph looks just like this one. But now because our velocity is in the opposite direction as our acceleration, even though we're going to start with a sorry, the computer's frozen. Sorry about that. Something wrong with Zoom. I think it's fixed though. So we're starting with a negative velocity. So that means we're starting with a negative slope, but it's decreasing towards 0. And then it's becoming positive. So it's really the opposite of this one here. Here we have a negative acceleration and a negative original velocity. So we start off with a negative slope. And it gets more negative, so it's going to get steeper like that. So I hope that makes sense. I wish I had started this one up here so that it fit all the other ones. But basically, when you have a linear velocity time graph, you're going to have a parabolic position time graph. If your slope is positive and your velocity is always positive, then you never do anything that gets steeper. If your slope is positive, but your velocity starts out negative, first you have to lose the negative, then you get steeper in the positive. And the same goes with the opposite direction as well. So if that makes sense, I hope problems like this could make sense too. We have a constant velocity here. That means as time is passing, our position is increasing linearly. Then our velocity starts to get steeper. So something like this happens. We get steeper. Then our velocity remains positive, but it starts to decrease. So something like that. So constant, getting steeper, getting shallower. It never goes back in the other direction because we never get below this axis. What would our accelerations look like? No acceleration, positive acceleration, negative acceleration. Let's try going the other way. I have a slope that's positive but getting smaller. So something that looks like this. Now I'm not moving at all. Time is passing, my position's not changing. So for this period of time, I have no velocity. Now a slope starts out shallow and gets steeper, but in the negative direction. Something like that. In both cases, I have a negative acceleration. I have no in the middle, but negative there. This is tricky. If you practice a bunch of these, I think you'll get it. We'll go over it more. And good luck. I hope this video helped.